Terence J. Sainowski, The Deep Learning Revolution, Artificial Intelligence Meets Human Intelligence. When you observe a toddler learning to recognize faces, it's easy to see they're not following complex rules in their brain about eye spacing or nose shape. They absorb thousands upon thousands of images, gradually building up their awareness. For decades, computer scientists tried the opposite approach. They wrote endless rules to teach machines what a face looks like, but the results were disappointing. Then, a small group of researchers had a radical idea. What if computers could learn like babies do? Instead of programming intelligence, what if we could grow it from data? This idea transformed everything. Today, your phone translates languages in real time, cars drive themselves, and computers beat world champions at games so complex, traditional programming alone could never master them. Voice assistants even understand your questions and respond in kind. You see, the revolution began in laboratories where neuroscientists and pioneering computer engineers worked side by side, studying how brains actually learn. The results, what scientists say took millions and millions of years, artificial intelligence achieved in a few decades. This blink tells the story of the development of machine deep learning to reveal both the power of biology and the surprising similarities between silicon chips and living neurons. The rebels of the 1980s. If you picture the AI world of the 1980s as a grand cathedral, everyone whispered the same prayer. More rules, bigger databases, faster logic. The high priest of artificial intelligence believed computers needed to think like philosophers, processing symbols and following rigid logical frameworks. If you wanted a computer to recognize a cat, you programmed it with rules about whiskers, pointy ears, and fur patterns. This approach appeared logical, even elegant. After all, humans could explain their reasoning, so surely machines should do the same. There was only one problem. It barely worked. While the AI establishment doubled down on symbolic reasoning, a small band of heretics gathered in the shadows. These researchers had a scandalous idea. Computers shouldn't think like philosophers at all. They should think like babies. Terry Sainowski was one of those rebels. Working alongside researchers like Geoffrey Hinton, he looked at the most successful intelligence system ever created and asked a simple question. How does the brain actually work? The answer was startling. Brains don't follow programmed rules. Instead, billions of simple neurons connect and reconnect, learning from experience. Think about riding a bicycle. You can't program the rules for balance, yet somehow your brain figures it out through practice. You fall, you adjust, you fall again, you adjust again. Eventually, your neural networks encode the patterns of successful balance without anyone writing a single rule. The AI rebels called this approach connectionism, and the AI establishment hated it. University funding dried up. Conferences rejected their papers. Critics dismissed neural networks as a dead end. They were too simple to achieve real intelligence. But the rebels noticed something. Nature had already solved every problem that stumped traditional AI. Birds navigate using vision. Babies learn language from hearing sounds, and animals recognize threats instantly. No programmer taught them these skills through the rules of logic. If the biological computer in every human head could master speech, vision, and complex reasoning, why couldn't silicon chips do the same? These early AI rebels were convinced that the secret lay not in better programming, but in better learning. They would soon discover they were right. But first, they needed to crack the code of how biological learning actually works. The answer should come from studying the most mysterious 3 pounds of matter in the known universe, the human brain. Learning from biology. Imagine learning to recognize your grandmother's voice on a scratchy phone line. Your brain doesn't consult a record of vocal pitch and accent patterns. Instead, something far more elegant happens. Millions of neural connections strengthen each time you hear her speak. while others fade away. Over time, your brain builds a unique fingerprint of her voice that works even through static. This is exactly what fascinated the AI rebel scientists like Sinowski and Hinton. They discovered that biological learning operates like a vast democracy, where simple neurons vote on what they're experiencing. No single neuron holds all the answers, but through their interconnection, they create intelligence. They began building artificial, programmed versions of these biological networks. They created mathematical neurons that could strengthen or weaken their connections based on experience, just like real brain cells. When they fed these networks thousands of examples, something remarkable happened. The artificial neurons organized themselves to recognize patterns without being explicitly programmed. Think of it like learning to spot your friend in a crowded airport. See, your brain doesn't follow a checklist of features. It processes the whole picture at once, combining height, walk, and posture into instant recognition. The AI rebels built networks that worked the same way, processing information in layers that gradually built up understanding. One breakthrough came from studying how the brain handles conflicting information. Real neurons sometimes fire randomly, almost like they're flipping coins. This seemed like a flaw, until researchers realized it was actually a feature. Randomness helps brains escape bad solutions and find better ones, like shaking a jar of marbles until they settle into the most efficient arrangement. Sinowski and Hinton captured this insight in something called a Boltzmann machine, named after a physicist who studied how particles find stable arrangements. These artificial networks could learn by trying different solutions and gradually settling on the best ones, just like your brain does when solving puzzles. But the real revolution came when they cracked the learning mechanism itself. They figured out how to make artificial networks adjust their connections automatically when they made mistakes, strengthening pathways that led to correct answers and weakening those that didn't. This process, called backpropagation, was like teaching a network to learn from its own errors. The key insight was profound. Intelligence wasn't about following rules, but rather finding patterns in massive amounts of data. Feed a biological brain enough examples, and it learns to see, hear, and understand. Feed an artificial network enough examples, and it could do the same. The breakthrough moment. For decades, the AI rebels had the right idea about how to advance machine learning, but lacked the raw power to prove it. Their neural networks were like Formula One race cars stuck with bicycle engines. They knew the design worked, but they needed much more fuel, bigger engines, and far longer racetracks to show what their machines could really do. Then three forces converged to make the perfect storm. First, computer chips became exponentially more powerful, especially graphics processors originally designed for video games. These chips could perform thousands of calculations simultaneously, exactly what neural networks needed. Next, the internet explosion created mountains of data. Every photo uploaded, every search query, every click of a mouse became training material for hungry algorithms. Finally, researchers refined their learning techniques, making networks deeper and more sophisticated. The breakthrough moment came when researchers fed massive data sets into these supercharged networks. Suddenly, artificial intelligence could do things that seemed impossible just years before. Consider what happened with image recognition. Traditional programming required engineers to manually code features like edges, corners, and shapes. It was like trying to describe every possible way to recognize a cat without ever showing the computer an actual cat. The results were mediocre at best. But when researchers fed millions of labeled images into deep neural networks, magic happened. The networks learned to recognize cats, dogs, cars, and faces with superhuman accuracy. They didn't just memorize the training images, they extracted the essence of what makes a cat, show them a cat they'd never seen before in any pose or lighting, and they'd recognize it instantly. Google Translate transformed overnight from a clunky phrasebook into a near-fluent translator. By analyzing millions of translated documents, deep networks learned the hidden patterns between languages. They discovered that concepts like love, freedom, and justice occupy similar positions in the mathematical space of different languages, even when the words sound completely different. Gaming provided the most dramatic proof. In 2016, a deep learning system called AlphaGo defeated the world champion at Go, an ancient strategy game more complex than chess. Go has more possible board positions than there are atoms in the observable universe. Traditional programming couldn't even begin to tackle such complexity, but deep learning thrived on it. Self-driving cars began navigating real roads, recognizing stop signs, pedestrians, and other vehicles in real time. Voice assistants started understanding natural speech and responding appropriately. Financial algorithms began spotting fraud patterns that human experts missed. The AI rebels had waited 30 years for this moment. Their networks finally had enough power, enough data, and enough sophistication to prove that machines could indeed learn like biological brains. The revolution was no longer theoretical. It was reshaping the world. What makes us human? Despite all the breathtaking advances in AI, one profound element remains missing. Current systems are like brilliant students who've memorized every textbook but have never stepped outside a classroom. They can recognize millions of images, translate dozens of languages, and defeat world champions at complex games, yet they lack something that every toddler possesses: direct sensory experience of the world. Now, consider how a 2-year-old learns. They crawl, touch, climb, taste, and explore. And when they learn the word hot, it's not a symbol in their vocabulary. It's connected to the memory of pulling their hand back from a scalding stove. This embodied learning creates a rich, interconnected, and deep understanding that current AI systems simply can't match. And that's because human intelligence emerges from our physical interactions with the world. We learn that objects fall when we drop them, that pushing harder makes things move faster, and that other people have thoughts and feelings different from our own. These seem like simple concepts, but they form the foundation of common sense, something that even the most advanced AI models struggle with. Now, if you ask a human why someone might carry an umbrella on a sunny day, they'll quickly suggest that rain might be expected later. Ask the same question to an AI system, and it might provide statistically probable answers without truly understanding the concept. See, humans excel at this kind of intuitive leaping because our learning is grounded in physical experience and social interaction. Emotions play an essential role in human intelligence, too. Fear helps us avoid danger, curiosity drives us to explore, and empathy allows us to understand others. Rather than being obstacles to intelligence, they're actually an integral part of it. They guide our attention, shape our memories, and influence our decisions in ways that logic simply can't. Perhaps most importantly, humans continue learning throughout their lifetime. A child who learns to walk doesn't simply stop adapting their movement when they encounter stairs, uneven ground, snow, or ice. They continuously adjust, building on previous experience while remaining flexible enough to handle new situations. The AI researchers who started this revolution understood something critical. Studying human intelligence wasn't about copying it, but understanding what makes learning possible in the first place. Today, the conversation flows both ways. Advances in deep learning are helping neuroscientists understand how our own brains work, while discoveries about biological intelligence continue to inspire new AI architectures. The gap between artificial and human intelligence remains vast, but it's narrowing. The question isn't whether machines will eventually match human intelligence, but what new forms of intelligence might emerge when silicon and carbon-based learning systems work together. The revolution continues. The deep learning revolution that began with a handful of rebels studying how brains work has become the defining technology of our time. Whether it enhances human potential or disrupts society depends largely on the choices we make today. The conversation between silicon and carbon intelligence has only just begun, and the next chapter of the story will be written by all of us together. Scientists are already developing systems that learn continuously, adapting to new situations without forgetting old ones. Medical AI can spot diseases in X-rays that human doctors miss, and climate models powered by deep learning can help predict weather patterns with unprecedented accuracy. Personalized education systems adapt to each student's learning style, making quality instruction available anywhere in the world. But this rapid progress brings profound challenges. In classrooms, students can now generate entire essays with a few keystrokes, forcing educators to rethink how they teach critical thinking and creativity. The technology that makes learning more accessible also makes cheating effortless. The job market faces similar disruption. AI systems already handle customer service calls, analyze legal documents, and create marketing content. While new jobs emerge in AI development and oversight, many traditional roles are disappearing faster than people can retrain. The challenge is more than just a technological one. It's human, too. How do we help millions of workers adapt to a rapidly changing economy? And perhaps most concerning is AI's ability to create convincing fake content. Deep learning can now generate realistic videos of people saying things they've never said, write news articles that sound authoritative but contain fabricated facts, and create social media posts designed to manipulate public opinion. When anyone can create believable lies at scale, distinguishing truth from fiction becomes a critical survival skill. Yet the same technology offers solutions. AI systems can detect deepfakes, flag misinformation, and help fact-checkers verify claims faster than ever before. The key lies not in curbing AI development, but ensuring it supports human flourishing. Looking ahead, researchers are working toward AI systems that combine the pattern recognition of deep learning with human-like reasoning and common sense. Imagine AI assistants that truly understand context, robots that learn by watching and asking questions, or medical systems that explain their diagnoses in terms doctors and patients can trust. The AI rebels who first looked to biology for inspiration gave us the tools to reshape intelligence itself. Now, it's up to all of us to use them wisely. In this Blink to the Deep Learning Revolution by Terence Sejnowski, you've learned that the journey from studying baby brains to creating AI traces one of the most profound shifts in human history. A small group of researchers who dared to challenge conventional wisdom discovered that intelligence emerges from recognizing patterns in vast amounts of data, not from following logical rules. Today, deep learning systems translate languages, diagnose diseases, and solve problems that seemed impossible just decades ago. Yet, as these technologies reshape everything from education to employment, we face important choices about how to harness their power while preserving what makes us uniquely human. The revolution that began by copying nature's most successful design now offers us the chance to thoughtfully guide the future of intelligence itself. Okay, that's it for this Blink. We hope you enjoyed it. If you